Welcome to Lecture 34, in which we will have a review of Test 32. Test 32 was calculating probabilities of different measurements for unentangled and entangled states, and we want to make sure that all of this is perfectly clear because this is definitely a problem that you will see. You'll see one similar to this on the final exam. And let's start, even though it's not absolutely necessary to approach the problem from the point of view of conditional probabilities, let's just start with a review of conditional probabilities. And this is a topic that we have talked about a little bit before when we talked about the idea of tossing two coins, and we said that if the coins were both fair coins and they were not connected with each other in any way, then the event of getting heads on the first coin and the event of getting heads on the second coin, those two events would be independent events. But if the coins were connected with each other in some way, then they would no longer be independent. And so we'll get back to that example in just a moment. But let's start off with a very fundamental idea from probability theory. And it says the following. We'll say A and B are two events, and A and B, or A intersect B, this is the event, or this is the case of both A and B. So, for instance, maybe event A is that a certain day falls in the month of March, and B is the event that it is raining on a given day, and so A and B would be the event that a day is a raining day, a day when it rains in March. And those would not be independent events, by the way, because it's more likely, it's not the likelihood of it raining in a given month does indeed depend on the month, so those would not be independent events. Okay, so the formula that I want you to be aware of here is that the probability that both A and B will happen is the probability of the probability that A will occur given that B has occurred times the probability that B will occur. And you can see easily that, of course, you could just switch the order of A and B and see that this is the same thing as probability of B given A times the probability of A. And this is a formula that is surprisingly useful. Now, so suppose that we had, returning to the coin example, and example, we'll say example or case one. Case one will be two unattached fair coins. So each coin is a fair coin, which means it has equal probabilities of landing heads or tails, and the two coins are unattached to each other. And so we'll define the four events. Actually, I'll just define two events here. H1 equals the event that coin number 1 lands on heads, and H2 will be the event that coin number 2 lands on heads. And so now we toss both coins, and we want to know what is the probability that both will be heads. If we toss both coins, what is the probability that both will land heads? And so we can use the formula from above to get the well-known result. So P, H1, and H2, we want both of them to be heads. And we can use the formula above. We have P of H1 given H2 times P of H2. Or, equivalently, we could use the formula P of H2 given H1 times P of H1. Either one of these formulas will give us the correct answer. And now let's think about them. What is the probability, looking here at this first expression, what is the probability of H1 given H2? So, given that the second coin lands on heads, what is the probability that the first coin lands on heads? Well, the fact that the second coin has landed on heads in this case has absolutely nothing to do with the first coin, because the two coins are unattached. So P of H1 given H2 is simply P of H1. It has nothing to do with what happens to the second coin. And then we bring down P of H2. And likewise, in the second form of the expression, this is the probability that the second coin lands on heads given that the first one lands on heads. Well, similar to what we've already said, the fact that the first one has landed on heads has nothing to do, it doesn't affect the second coin at all. So P of H2 given H1 is just P of H2. And then we bring down the P of H1. And so we see that the two formulas give exactly the same result. It's just the two probabilities multiplied by each other. And since these are fair coins, this would be 1/2 times 1/2, which is 1/4. And of course, that's a very familiar result. Now let's look, though, to see how this can explain another case. Let's say two fair coins attached as follows. Let's say that this is one coin, and we'll have an attachment now. Here's the coin number 1, and it's attached so that when its head is up, then on coin number 2, its head is up. And so now, if we toss these connected coins, what is the probability both will land heads? And again, we can use the formula. So we have P of H1 and H2 is equal to P of H1 given H2 times P of H2. Well, we could also use the other form of the equation, but let's just stick with this, as only one is needed. So, now let's think about this carefully. What is the probability that the first coin will land heads given that the second has landed heads. Well, if the second coin has landed heads and the coins are attached in this way, then the first coin must land heads. So this first probability here simply becomes 1. And then the probability that the second one lands heads, since it's a fair coin, that's 1/2. And so now our probability that both would land heads is 1/2. And of course there's also a 1/2 probability that both would land tails. And finally, although I won't write it out, you can think of a case number 3 where suppose that they were connected so that when the one was heads, the other one would be tails. Well, we know from common sense thinking that if they were connected in that way so that when the heads showed on one and the tails showed on the others, we know that from common sense type thinking that the probability that both would land heads then would be 0. But how do we figure it out with this formula? Well, we would say P of H1 given P of H1 and H2. We'd still use this same formula, but then P of H1 given H2 would be 0 because that's the probability that the first one lands heads given that the second one has landed heads. But if the second one has landed heads, there's absolutely no probability the first one will also land heads because they're connected so that when the heads of one shows up, the tail of the other one shows up. So this would be 0 here. This would still be 1/2, and 0 times 1/2 would give us 0. So that would be how we would handle that case. So this is a simple example of the use of conditional probabilities. And now let me show you one. This is a problem I've given on tests before in other classes, and I think it's sort of an interesting problem. And I'm going to show you the problem. It's pretty straightforward. I'm going to show it to you, let you stop the video for a few minutes, try it on your own, and then I'll show you a couple of ways of solving it. So the problem is the following. And this I found a problem like this originally in a rather old textbook, and so it was back in the days when a fairly large number of students smoked, and so I'll just I'll keep their problem. This is not exactly the numbers they use, but it's fine. But anyway, the problem goes like this. So at a certain college, 60% of the students are female and 40% are male. Also, 70% of the male students smoke, while 40% of the female students smoke. If a student is picked at random and is found to be a smoker, what is the probability that the student is a male? So I'd strongly encourage you to stop the video for a moment and try that problem for yourself, and then check back and see, compare your answer with what we'll get. Okay, so I hope that this problem was interesting to you, and I hope that you found it not too difficult. And I want to talk to you now about two approaches. First, the first one I'll call sort of a common sense approach. And this is by far the one that I see most often from students when they attempt a problem like this on a test. They would start by supposing there are 100 students. Okay. Now, if there are 100 students, then you would have, according to the given information, you would have 60 female students and 40 male students. Now, of those females, 40% of the females smoke. So you would have 24 female smokers and 36 female non-smokers. And for the males, the probability that a male student smokes is 70%. So of those 40 males, you would have 28 male smokers and 12 male non-smokers. And just to check our math to make sure that this should all, for these 100, this should add up to the total 100. So let's see, 12 and 36 would be 48. 48 and 24 would be 72. 72 and 28 is indeed 100. So here would be our 100 students. And now we're supposing that a student is picked at random and is found to be a smoker. So that means that we are in this group of students over here on the left-hand side, this group that consists of 24 females and 28 males. And so you can see the probability, the desired probability very easily. It will be P is equal to, we want to know the probability that it's a male, and that would be 28 over 24 plus 28, which is 28 over 52. The total number of smokers here, total number of smokers is 52, and of those, 28 are male. So we have 28 over 52, and if we divide top and bottom by 4, we get 7 over 13. So this is the probability that you would reach from a sort of a common sense approach. Now I'd like to show you how to approach this problem using conditional probabilities. So we'll say conditional probability approach. And since it's off the screen, I'll just write our formula once again. Remember that our formula that we're using over and over is that the probability of A and B is equal to the probability of A given B times the probability of B, which is also the same as the probability of B given A times the probability of A. So, let's try to figure out now what the situation is. What are we really trying to find? Let's let M be the event that a student is male. F be the event that a student is female, and S be the event that a student smokes. Okay, so we have a student who is a smoker. That's given now. We know that the student is a smoker, and we want to find the probability that the student is a male. So what we are trying to figure out here is P of M given S. Now, if you look at our general formula here that we're using over and over, you can see that this implies that P of A given B is equal to P of A and B over P of B. So using that formula, then, we have that the probability that the student is a male, given that the student is a smoker, is equal to the probability that the student is a male and a smoker divided by the probability that the student is a smoker. Now, the expression in the bottom is easy, actually. The probability that a student is a smoker is actually equal to the probability that a student is a smoker, given that the student is a female, times the probability that the student is a female, plus the probability that the student is a smoker, given that the student is a male, times the probability that the student is a male. That's the total probability that the student is a smoker. But what about the expression in the top? The probability that the student is a male and a smoker. Well, that's a combination of two events, and we can't simply say that it's a probability that it's a male times the probability of a smoker, because that would imply that these are independent events, but they're not independent, because we see that the percentage of smokers among males is different from the percentage of smokers among females. So how are we going to evaluate this expression in the top? Well, we can look to our formula once again. Now remember, in getting this first part of the equation here, we've already used this formula once, and now we're going to use it again. P of M given S is the same as P of S given M. Well, I think I said that incorrectly. I should have said P of M and S is equal to P of S given M times P of M. And this is, again, just using this formula. And now we're ready to finish this problem. Let's see how it goes. The probability that a student smokes, given that the student is male, we were told that 70%. 70% of males smoke. The probability that the student is male, that's 40%. The probability that the student smokes, given that the student is female, well, 40% of females smoke, so that's 0.4. And the probability that a student is a female is 60%. And then the rest of this, notice, is just exactly what we have in the top. So 0.7 times 0.4. And so we have 0.28 over 0.24 plus 0.28 which is 0.28 over 0.52, which is 7/13, just as we found before. But this, in this case, we used conditional probabilities. So that's a brief review of conditional probabilities, and it's actually a little more in-depth view than what we said before in one of our earlier lectures. But now let's connect this all to test 32 now. Actually, maybe I won't put maybe I won't put this quite yet, because I want to talk a little more generally before we get down to the details of 32. So let's write it like this: any 2-qubit state C can be written as C equals A 0 0 plus B 0 1 plus C 1 0 plus D 1 1. Okay, and now if Alice measures the first qubit with the standard basis, and Bob measures the second qubit with the standard basis, then we can say the following. Well, actually, let me change this. And if we use the following definitions of events, and we're going to define our events as follows. We'll say A0, A1, B0, B1. A0 is the event that Alice measures 0. A1 is the event that Alice measures 1. B0 is the event that Bob measures 0. And B1 is the event that Bob measures 1. If we define events in that way, then what we can say is the following. Then P of A0 and B0 equals A conjugate. P of A0 and B1 equals B conjugate. P of A1 and B0 equals C conjugate. And P of A1 and B1 equals D conjugate. So if A, B, C, and D are all positive, or let me rephrase that a little, are all known to be positive real numbers, then A is the square root of P of A0 and B0. B is the square root of the probability of A0 and B1. C is the square root the probability of A1 and B0. And then finally D is the square root of the probability of A1 and B1. Now, if we apply our formula that we learned above about conditional probabilities to each one of these cases, we will get A equals the square root of P of B0 given A0 times P of A0 here. And of course, now that could also be written as P of A0 given B0 times P of B0. But you already know that, so I'm not going to expand on that. But I will say then that this is equal to the square root of. Actually, well, we can simplify this, but maybe there's no sense of belaboring this point. All of you can do algebra, so I'll just leave it at this. And so B would be square root of P of B1 given A0, P of A0, C is the square root of the probability of B0 given A1, P of A1, and finally D is square root of the probability of B1 given A1 times the probability of A1. And once again, we can we can manipulate these algebraically and make these expressions a bit different, but those are the results we would get for A, B, C, and D, provided that we know that A, B, C, and D are all positive real numbers. Now let's go back. Instead of talking about probability, again, let's return to the physics and see what we can do with that. Okay, keep in mind we have C. We wrote down that C is equal to A 0, 0 plus B 0, 1 plus C 1, 0 plus D 1, 1. And and let me stress, this is for, I want to say again, as was written here, this is for any 2-qubit state. It doesn't matter if it's entangled or unentangled. So let me just put that note. Any, whether entangled or unentangled. So we're making no assumptions about whether or not the state is entangled at this point. And likewise, in what we're about to do, we still make no assumptions. Okay, so we'll say whether C is entangled or unentangled, we can write this as, okay, and this is a review of something we've done before. We could, if we factor out that the first qubit, we can have 0 times A0 plus B1 plus C1 times, should be just 1, times C0 plus D1. We've made this kind of manipulation before, and then what we do is for each parenthetical term we normalize it, and so we get square root, and again now continue to work with the assumption, assuming A, B, C, and D are all positive real, just to keep this a little simpler. So this would be square root of A squared plus B squared, 0, and then we have A0 plus B1 over square root of A squared plus B squared plus the square root of C squared plus D squared 1 times C0 plus D1 over square root of C squared plus D squared. And when we write the state in this form, it allows us to gain some more insight into what's going on. We now see that the probability that Alice measures 0, so this is A0. Okay, this is Alice measuring 0, and this is Alice. Well, this is the first qubit being 0. This is the first qubit being 1, and so the probability that Alice measures 0 is simply this squared. So it's A squared plus B squared. The probability that Alice measures 1 is equal to this squared, which is C squared plus D squared. Now, what are these probabilities in here? Well, let's look at the probability that Bob measures a 0 given that Alice measures 0. Okay, Alice measuring 0 means we're talking about this term, and the probability now that Bob measures 0 given that Alice measures 0 is A squared Remember, we need to square this coefficient of the 0. So we have a squared over a squared plus b squared. The probability that Bob measures 1, given that Alice measures 0, is b squared over a squared plus b squared. The probability that Bob measures 0, given that Alice measures 1, is c squared over c squared plus d squared. And finally, the probability that Bob measures 1, given that Alice measures 1, is d squared over c squared plus d squared. And now, one thing I'd like to point out to you is that all of these equations that we've written here are consistent with what we have up here. In other words, for example, we'll say, note that these equations are consistent with those from above. For example, okay, we know that from our basic formula that P of B0 given A0 times P of A0 should be equal to P of A0 and B0. That's from our basic formula, probability formula that we've been using over and over. And now let's check and see if that's true. Well, according to this formula here, P of B0 given A0, so we'll say check this. Okay, P of B0 given A0, according to this formula, is A squared over A squared plus B squared. P of A0 is A squared plus B squared. And so that's what this is equal to. And on the other hand, P of A0 and B0, here we'll go to the formula above. P of A0 and B0 is here under the square root, so if we square both sides of this, we get P of A0 and B0 is A squared. And indeed, we can see that these two are indeed equal to each other. So I'll put a check mark over that. And you could check other possibilities as well. Now the only remaining thing I think to do, okay, let's go ahead and circle all of these equations because they're all potentially useful in solving problems such as those found on test 32. But there's one more thing I'd like to point out before we actually start talking specifically about that test. Okay, let's start again with C equals A00 plus B 0 1 plus C 1 0 plus D 1 1, and the assumption again, A, B, C, and D all positive real. And again, that assumption is made just to make things easier. And now, instead of factoring out the first qubit, we'll factor out the second qubit. So to do that, the first step will be to rearrange these terms. We'll have A 0 0 plus C 1 0 plus B 0 1 plus D 1 1. And now we see that this can be written as A 0 plus C 1 times 0. And of course, it's not really times, but it's tensor product. And then here we will have B 0 plus D 1 tensor product with 1. And now, just as we did before, we will normalize the parenthetical expressions. So we get A 0 plus C 1 over the square root of A squared plus C squared. And then we'll have 0 and square root of A squared plus C squared plus B0 plus D 1 over square root of B squared plus D squared 1 square root of B squared plus D squared. And so when we write C in this way, we see that probability that Bob measures 0. See, notice before we got probability, since we had factored out the first qubit, we got probability of what's going on with Alice, but now that we've factored out the second qubit, we can get the probabilities for Bob. So probability that Bob measures 0 is this squared, so we have A squared plus C squared. Probability that Bob measures 1 is B squared plus D squared. And we can also talk about conditional probabilities. Probability that Alice measures 0 given Bob measures 0 is A squared over A squared plus C squared. The probability that Alice measures 1 given that Bob measures 0 is C squared over A squared plus C squared. The probability that Alice measures 0 given that Bob measures 1 is B squared over B squared plus D squared. And then finally, the probability that Alice measures 1 given that Bob measures 1 is D squared over B squared plus D squared. And so here are still other formulas that we could use to solve problems like those on test 32. So I believe that Now, there is actually one more thing we're going to need to say in a bit, but let's go ahead and try to tackle our problems. So the first set of problems on the test 32 centered around the situation here. It was stated, consider the state C equals A00 plus B01 plus C10 plus D11, where A, B, C, and D are all real positive numbers. So that's exactly the situation that we've been talking about today in this lecture. And Alice measures the first qubit using the standard basis. Bob measures the second using the standard basis. And again, that matches what we've been talking about in this lecture. And now we're told that if Alice measures a 0, the probability that Bob measures 0 is 30%. If Alice measures 1, then the probability that Bob measures 0 is 40%. And we have some questions. Now, as was explained in class, this first one is really very straightforward. It says which statement is true. C must be entangled, C must be unentangled, or the last choice is the information given is insufficient to determine whether C is entangled or unentangled. And the answer is A. And the reason for that is that the probability that Bob measures 0 is different if Alice measures 0 from what it is if Alice measures 1. It's 30% in one case and 40% in the other. So that means that what Alice measures has an effect on what Bob measures. And that is true only for an entangled state. It is not true for an unentangled state. For an unentangled state, the two measurements are completely independent. So the answer to 32.1 is definitely A. Now, for the rest of this problem, we are given one more piece of information. The information we've had so far is still true, but now we're given one more piece of information, which is to assume for the remaining problems that the probability that Alice measures 1 is 60%. Now, I'll call to your attention now that we're given basically three pieces of data here. If Alice measures 0, the probability that Bob measures 0 is 30%. If Alice measures 1, the probability that Bob measures 0 is 40%. And the probability that Alice measures 1 is 60%. We have three pieces of information, and we'll compare that to the situation we'll consider next in just a moment. But let's think about these three pieces of information that we have in this set of problems before jumping to the next situation. Okay, so let's use the notation that we have been developing to get a better grasp on how to approach this problem. Okay, the first thing we're given is that if Alice measures 0, then the probability that Bob measures 0 is 30%. So that's saying P of B0 given A0 is 0.3. The probability that Bob measures 0 given that Alice measures 0 is 30%. Okay, that's what this statement means. Now the next one. If Alice measures 1, the probability that Bob measures 0 is 40%. So this is P of B0A1 equals 0.4. So both of those are conditional probabilities. And then we have one more statement here, one more piece of data, which is that the probability that Alice measures 1 is 60%. So P of A1 is equal to 0.6. And we will see that these three pieces of information plus one more observation will be enough for us to finish this problem. Let's maybe go ahead and make that observation right now. And the observation is as follows. Alice, of course, can only measure a 1 or a 0. And we're told that the probability that Alice measures 1 is 0.6. So that means that by default, the probability that Alice measures 0 is 0.4. And that is being deduced now from this information right here, that the probability that Alice measures 1 is 0.6. Okay, now equipped with these four equations, we will now try to find A, B, C, and D. And it actually will be quite easy if we go to this set of equations that we've circled right here. P of A0 is A squared plus B squared. And down here we have P of A0 equals 0.4. So A squared plus B squared is equal to 0.4. P of A1 equals C squared plus D squared. And here we have P of A1 equals 0.6. So C squared plus D squared equals 0.6. And notice that the fact that A squared plus B squared plus C squared plus D squared adds up to 1 should not be surprising at all, because those are the four coefficients here for C. Okay, now let's go to these. We have now used these last two equations to get some information about A, B, C, and D. Now what about these first two equations? What is P of B0 given A0 and P of B0 given A1? Well, up here we have the answers. P of B0 given A0 is A squared over A squared plus B squared. A squared over A squared plus B squared. So A squared over A squared plus B squared is 0.3. That's P of B0 given A0. And what about P of B0 given A1? P of B0 given A1 is C squared over C squared plus D squared. So C squared over C squared plus D squared. That is P of B0 given A1, and that is 0.4. And so now we will see that this problem, once we've made these observations, this problem is trivial, because if we take the first equation and the third equation and put them together, then we will have A squared divided by A squared plus B squared, which is 0.4. And that's equal, according to this, A squared over A squared plus B squared is 0.3. And therefore A squared is equal to 0.12. And A, so we can write up here, A equals square root of 0.12. And notice that this immediately gives us B squared, because if we substitute 0.12 in for A squared, then we get B squared is 0.28, or B equals the square root of 0.28. And now if we combine the second equation and the fourth equation, we have a similar kind of situation. We know that c squared plus d squared is 0.6, and here we have c squared over c squared plus d squared is 0.4. So that tells us c squared over 0.6 is equal to 0.4, which says that c squared is 0.24, and therefore we come up here, c is the square root of 0.24. And what about d? Well, we plug in the fact that c squared is 0.24, plug that in here. So 0.24 plus d squared is 0.6. That means d squared is 0.36. So d is the square root of 0.36. And that is how we can easily solve the first 5 problems in test 32. And by the way, these answers, in case you did turn in your test last time, you'll notice that these answers all match what was on the key. So I hope that that clarifies completely how to approach that problem. And so now let's consider the second situation that appeared on test 32. So here is the second situation we considered on test 32. And here we are explicitly told that in this second situation, the state is unentangled. And the state is given by the same expression as we had before, where again A, B, C, and D are all real positive numbers, and Alice measures the first cubit with the standard basis, Bob measures the second with the standard basis, so all of that is the same. But the difference now is that instead of being given 3 equations, 3 pieces of data, it appears that we're only given 2. We have the probability that Alice measures 0 is 25%, and the probability that Bob measures 1 is 60%. So we have P of A0 is equal to 0.25, and we also have P of B1. Actually, I'll put this over here. P of B1 equals 0.6. Now, of course, we can use these 2 pieces of information to deduce another couple of equations. Just as we did in the previous problem, we can say that Alice can only measure a 0 or a 1, so if her probability of measuring 0 is 25%, then her probability of measuring 1 must be 75%. So we can say P of A1 is equal to 0.75. And likewise, Bob can also measure only a 0 or 1. So if his probability of measuring 1 is 0.6, then his probability of measuring 0, P of B0, must be 0.4. So we have all of that, and if we look at our equations up here, okay, the P of A0 is A squared plus B squared, and P of A1 is C squared plus D squared. So we have A squared plus B squared equals 0.25, and C squared plus D squared is equal to 0.75. So that's how we can use these first two equations. And then the second two, okay, P of B0, if we scroll up here, P of B0 is A squared plus C squared, P of B1 is B squared plus D squared. So we have A squared plus C squared is equal to 0.40, and B squared plus D squared is equal to 0.6. Now, to be honest, what I think I would do, the first thought I might have to trying to solve this problem is to say, well, we can think of A squared as one unknown, B squared is another one, C squared is another one, and D squared is another one. So we have 4 equations and 4 unknowns. And so unless those 4 equations are dependent equations, we should be able to solve the problem. Let's try to do that with Gaussian elimination. So we have 1, 1, 0, 0 will be the first row of our matrix. What I'm thinking of here is I'm putting these 4 equations and 4 unknowns in a matrix form. So I'll have here A squared, B squared, C squared, and D squared. And 0.25, 0.75, 0.4, and 0.6. And then the second equation would be 0, 0, 1, 1 to give C squared plus D squared equals 0.75. The next one would be 1, 0, 1, 0 to give A squared plus C squared equals 0.4. And then finally 0, 1, 0, 1 to give B squared plus D squared equals 0.6. And so if you remember from your algebra courses, linear algebra courses, how you would try to solve this problem. Of course, one way would be with determinants, but I'll just use Gaussian elimination. So we'll say 1, 1, 0, 0. This is what they call the augmented matrix approach, in case you have seen that terminology before. 0, 1, 0, 1. And then 0.25, 0.75, 0.4, and 0.6. And now we add the negative of the first row. If you don't know what I'm doing here, don't worry about it. You can just plug it into your calculator and see what happens. But I'll just explain to you what I'm doing as I go along. So if I add the negative of the first row to the third row, I can get rid of this 1. So let's do that. So we'll have 1, 1, 0, 0. and we're not going to bother the second row yet at all. So 0, 0, 1, 1, 0.75. But as I said, we're going to add the negative of the first row to the second row to get rid of this 1. And so we get 0, negative 1. Negative of 1 to 1 is 0. Negative 1 and 0 is negative 1. And then we'll have 1, 0. 1, 0. And negative 0.25 added to 0.4 leaves 0.15. And then the last row stays as 0, 1, 0, 1, 0.6. And now what I will do is the next step, I will leave the first row as it is, 1, 1, 0, 0, 0.25. And I will interchange the second row and the last row. So the second row now becomes 0, 1, 0, 1, and 0.6. The third row remains 0, negative 1, 1, 0, and 0.15. And now the new fourth row is the old second row, so 0, 0, 1, 1, 0.75. And continuing. Now we want to get rid of all the ones, all the non-zero terms below the diagonal in this column. We've already done that in the first column. Now we want to do it in the second column. And the only one below the diagonal in the second column is this negative 1, which is easily eliminated by adding the second row to the third row. So we get then 1, 1, 0, 0, 0.25, 0, 1, 0, 1, 0.6. And then when we add the second row to the third row, 0 and 0 is still 0. 1 and negative 1 is 0. 0 and 1 is 1. 1 and 0 is 1. And 0.6 and 0.15 is 0.75. And then we write our last row, and you see what's happening here. Our third row and our fourth row are the same. So this means that, if you have experience, you realize you can go ahead and stop now and say that these equations are dependent equations. But if you don't see it quite yet, just go one more step. Let's now add the negative of the third row to the fourth row, and we will get 1, 1, 0, 0, 0.25, 0, 1, 0, 1, 0.6, and 0, 0, 1, 1, 0.75, and 0, 0, 0, 0, 0 when we add the negative of the third row to the fourth row. So what this is telling us is that the original system of equations, the original system of 4 equations in 4 unknowns was a dependent system. It is equivalent to the independent system a squared plus b squared equals 0.25. b squared plus d squared equals 0.6, and c squared plus d squared equals 0.75. Which, of course, is 3 equations. In 4 unknowns. So, this is not enough. This is insufficient to find a squared, b squared, c squared, and d squared. So what do we do? Let's go back up here and think about this for a couple more minutes. Now, again, we used the fact that the probability that Alice measures 0 is 25%. That's right here. And from that, we deduced P of A1 is 75%. The probability that Bob measures 1 is 60%. We used that here and use that to deduce this, and then these 4 equations became these 4 equations, but we found out after some analysis that these 4 equations are really not 4 independent equations. They are equivalent to 3 independent equations. So we have 3 equations and 4 unknowns, and so we just can't find a squared, b squared, c squared, and d squared unless we have something else. Now, and notice that all the information given here includes absolutely no information about conditional probabilities. So when you come up here and look at the equations that we deduced before, we have, for instance, these 2 equations, and we've used them down below, but we don't have any information about conditional probabilities. And likewise up here, we've used these 2 equations, and we don't have any information about conditional probabilities down here either. So it looks initially like we're stuck until we look at this problem one more time and see that we're overlooking one critical word, and that is the word unentangled. Unentangled. And the fact that this is unentangled makes this actually very easy. So how does that happen? Okay, this is what we know down here. But we have not, this is before we use the fact that it's unentangled. Now let's include that one extra fact. And it's important for you to know, to understand now. If we did not have that word in there, if we did not know that this state was unentangled, then we could not solve this problem. But let's see how the fact that it is unentangled will help us out. Well, remember that since the state is unentangled, P, let's look at some of these conditional probabilities that we have up here. Let's look at our first set of circled equations. We have P of B0 given A0. In fact, let me just copy and paste all 4 of these equations right here. And so let me actually I want to get rid of this part first, because what I'm copying and pasting, of course, applies for any kind of a state. So let's paste that. Oops, sorry. Didn't take. I'll try again. Oh, now what is this my problem? Since I'm having a little technical difficulty, let me pause this for just a moment and we'll get this straight. Okay, so sorry about that interruption. But here are the four equations that we had. This was the first in the first group of circled equations up here. We could also use those from the second group. So the ones that I've copied are these four, which is the first group of circled equations, but we could just as well, wait, sorry about that. This is, the ones I copied were from right there, and I have uncircled them thinking that that was the problem in copying, but I don't believe it was. It was something else. It was the fact that my keyboard was not connected. But anyway, so here's that first group of circled equations, and I copied these four down below, but we could have just as well used these four equations. It wouldn't matter, as you will see. And remember again now that those four equations, in fact, I want to remind you, so we'll say recall that for any state, whether it is entangled or unentangled, we have these four equations are true. But now we incorporate the critical information that this state is entangled. So, but for unentangled, the state we're dealing with now in this problem is unentangled. But for unentangled states, we have P of B0 given A0 equals P of B0. P of B1 given A0 equals P of B1. P of B0 given A1 equals P of B0, and P of B1 given A1 equals P of B1. This is just saying that what Bob measures is independent of what Alice measures. So, for instance here, this probability that Bob measures 0, given that Alice measures 0, well, the fact that Alice measures 0 has no effect on the probability that Bob measures 0. It's just, so the probability Bob measures 0 is the probability Bob measures 0. Unlike in the first case, where Alice's measurement did affect Bob's measurement, in the second case here, where we have an unentangled state, those measurements are independent. And so now we have more equations that we can use, and let's see if we're now ready to to finish this problem. Okay, so let's use this first equation. Okay, P of B0 given A0 for any kind of state, whether it's entangled or unentangled, that's A squared over A squared plus B squared. So we have A squared over A squared plus B squared. And that is equal to P of B0. And we have found out up here that P of B0 is 0.4. And the second equation, P of B1 given A0, that's actually, well, we can use that one. I'll go ahead and put it down. So P of B1 given A0, this is B squared over A squared plus B squared. So B squared over A squared plus B squared. And that's P of B1, and P of B1 is 0.6. And let's go ahead and look at these two equations. P of B0 given A1, well, P of B0 given A1 is C squared over C squared plus D squared. C squared over C squared plus D squared. And that is 0.4 because it's P of B0, and we've already identified that as 0.4. And finally, P of B1 given A1 is D squared over C squared plus D squared, and that is 0.6. But, and this is where we will now be able to finish this problem, A squared plus B squared is 0.25. So we have then that A squared over A squared plus B squared, which is 0.25, equals 0.4. B squared over 0.25 is 0.6. C squared over, now notice up here we have C squared plus D squared is 0.75. So C squared over 0.75 is 0.4. And D squared over 0.75 is equal to 0.6. And you come up then with the conclusions. A squared is equal to 0.25 times 0.4, so that's 0.1. B squared is equal to 0.25 times 0.6, so that's 0.15. C squared is equal to 0.75 times 0.4, which is 0.3. And D squared is 0.75 times 0.6, which is 0.45. And as a check, let's make sure that all these add up to 1. We would have 0.45 and 0.3 is 0.75, and 0.15 would be 0.9, and 0.1 is indeed 1. And so our final answers are A equals square root of 0.1, B equals square root of 0.15, C equals square root of 0.3, and D equals square root of 0.45. And those are your answers. Those, again, these were the answers that were given on the key in class. These are for the last 4 problems right here on test 32. So that gives a complete working of test 32 and relates all of this to the ideas of entanglement and unentanglement, the ideas of conditional probabilities, And so I hope that this ties that all together, because these are definitely important concepts which you should expect to see again on the final exam. And so now let's consider some problems, some more problems related to these ideas. Okay, so I've given a lot of thought to these in-class problems, and I've come up with something that I hope will really challenge all of you, even those who were able to solve the last test, test 32, without any difficulty. I think that this ramped up the difficulty now, and let's see what you can do with this. And I really encourage you to give this an effort. So anyway, the problem says the following. We have an unentangled state, C, which is equal to A00 plus B01 plus C10 plus D11, where, as usual, A, B, C, and D are real positive numbers, and Alice measures the first qubit using the standard basis, and Bob measures the second using the standard basis. Now, what you're given this time is the probability that Alice measures 0 and Bob measures 0 is 0.12. The probability that Alice measures 1 and Bob measures 1 is 0.32. And finally, you're given this last bit of information, which may seem a little mysterious. It says the probability that Bob measures 1 is less than the probability that Alice measures 1. And I will say that that is necessary information if you... this is necessary information if you want to actually solve with certainty for A, B, C, and D. And it's an interesting problem to see why that last piece of information is necessary, but I don't want to say any more because I don't want to give this away. So those are your in-class problems, and then we'll have in-lecture problems, and then we'll have something in class as well. But that finally, I know it's been a long one, but I think it's worth it because these are definitely important ideas. So that concludes lecture 34, and good luck.